So I've discussed the Fourier series and how you can compose and decompose any sort of signal into sine waves. Now I'm going to discuss something called an RC network. R stands for resistance and C for capacitance. So it's a resistor and a capacitor, and they work together to do all sorts of things. You can create timing circuits and filters and everything. Even bypass capacitors are a sort of RC network. So let me briefly show you what one is. An RC network is just a resistor and a capacitor. We'll go ahead and illustrate this using a simple switch. This is the simplest RC network, just a capacitor, a resistor, and that's it. Now recall what a capacitor is. A capacitor is two conductors with an insulator in between, and it's usually very close because you want charges to be able to reach each other with their force. So they have to be close enough, but you don't want to actually conduct. So you want just enough insulator to insulate. So what happens if you apply a positive here and a negative here, no current flows through the capacitor, but essentially, once again, not getting too deep into physical details, but the negative side exerts a sort of push, electromotive force push, of the electrons into here, and the positive side sort of pulls on them. Now normally that's going to do nothing. They'll bunch up a tiny bit through the wires, and then they'll just stop because they have nowhere to go. Because the desire, quote unquote, for these electrons to not bunch up together or be too far apart is much stronger than whatever voltage you're applying. So they won't cross the insulator unless you have a gigantic voltage that's called lightning. But when the insulator's thin enough, even though the electrons don't really go over, other than once in a while, they're still pushing. The force of them pushing can just barely reach over there. So you get excess electrons on this side, and then the electrons scatter. So you essentially have imaginary positive charge carriers here, sort of like how they talk about electrons in holes and transistors. There's no positive charge carrier in wires. The charge carriers are electrons, but this is what they would mean by holes. There is a positive charge here and a negative charge here. And the funny thing is, this negative charge resists more negative charge going in, and it would try to pull the electrons back up, but it's actually pulling on this positive charge. So an electron over here might try to get back through here, and it's entering this big old positive area, but then you've got this negative area here that roughly balances it, so it shoves it away again. So they try to balance in and balance out. So it's this weird dichotomy of, there's a positive charge here. Electrons should be getting in, but the electrons here are pushing them away. And the positive charge here is holding these electrons here, so they don't spread back out that way. It sort of gets glued in there. That's how a capacitor holds its charge. And it does discharge naturally over time. Some electrons sneak across, and some of them bounce away. Some electrons get in there and stay, and so over time, it does discharge. But the point is, you should be able to see that the more electrons get shoved into here, the harder it is to push more in. You need more voltage because there's already a bunch. So what you get is a diminishing charge. When this is empty, you can shove electrons in there pretty easy with a decent voltage, but then it stops wanting to go in and starts resisting. It'll keep going in until this voltage across here matches the outside voltage, but it happens more slowly. So you get a curve. So when you close this switch, you've got positive here pulling, negative here pushing, and the capacitor charges, but it's limited by the resistor. If you didn't have the resistor here, it would work, but you'd have a short circuit and things would catch fire. So the resistor limits the current, and the capacitor limits the current, and so you get a curve based on the resistance and the capacitance. That's why it's called an RC network. It's all about the time. So let me put this over here in an easier to see way. Let's do positive, resistor, switch, capacitor, and negative. That'll be a little easier to work with. Give me more room. So let me draw a plot. This axis is time. This is where we start and time goes forward. And this axis is voltage. This is the charge on the capacitor, the charge on that capacitor. Right now, we start around 0. We close the switch. The capacitor starts charging rapidly, but as the capacitor gets more and more charged, there's less of a voltage difference. If this is 5 and this is 0, that's 5. If this is 5 and this has gone up to 3, that's 2. So there's less force pushing it in, opposing the electrons that are already down here. So it's trying to push more in, but it's harder to do so it takes more time. So the curve ends up looking like this. At the start of time, the voltage increases rapidly, and eventually it flattens out and approximately reaches 100%. There's a spot here we call tau. It's just a Greek letter, lowercase t essentially. And this is around 68 or something percent. Notice I said percent. I forget exactly what percentage it is, it doesn't matter. Unless you're doing math on it, we'll go into that later if we need to. But you'll notice I said percent. It doesn't matter what the voltage is at all. 0 to 5 volts, 0 to 100 volts, 0 to whatever. 68 or so percent. Tau equals RC, R times C. So this is C, this is R. We know what V is. Let's not be confusing. Resistance is in ohms. Capacitance is in farads. If you multiply those, you get seconds. Tau, R times C, is the amount of time, regardless of the voltage, that this circuit with this resistance and this capacitance will charge this capacitor to about 68-ish%. And 5 tau, 5 times tau, we say is 100. It's of course not. Nothing's ever perfect. We're rounding again. Surprise, surprise. But 5 time constants, 5 of those tau, is widely accepted by the entire electronics community to be close enough to 100% that we say, okay, it's charged. 5 tau is the fully charged from 0 to close enough to 100%. And the opposite. That's the discharge time as well. If you have one that's fully charged, 5 tau will get it down effectively to 0. And unsurprisingly, that graph looks similar. It will decrease rapidly because, let's say, this is charged to 5 volts and you are putting 0 volts in the circuit with it. That's how you discharge. You have a lower voltage. So it decreases rapidly, but now let's say it's 2 volts and then you've got 0 volts. So there's less of a push because the voltage is pushing across the resistor. And it's the same thing. It goes to about 0 at 5 tau. So this is the magic of an RC network. You have whatever your resistance is, whatever your capacitance is, and if you have multiple resistors and capacitors, you can just combine them into effectively one series and parallel functions until you get down to just one resistor and one capacitor. Multiply them, you get seconds. Multiply them by 5, and that's how long roughly it's going to take to charge your capacitor or discharge your capacitor after you've charged it. And this is used to decide frequencies of things, like if you're applying a square wave, 5 volts, 0 volts, 5 volts, 0 volts, to charge and discharge a capacitor, you know what the frequency of that square wave should be if you want it to fully charge and discharge, or partially, or whatever. That's why we have this. Now, one quick thing I'd like to show you, a little bit of math, it'll be quick, is the units. Because the first time I saw this, I thought it was dark sorcery. How do you take ohms and farads and multiply them to get seconds? What in the world do resistance and capacitance have to do with each other? Physics is weird. Let me show you. So we have tau, that's pi. We have tau equals resistance times capacitance, or seconds equals ohms times farads. Now that's the funny thing about these units, is you can multiply and divide units as if they were variables. You don't actually do math with units. It's only multiplying and dividing that you can do. It just works out that way. So like, for example, if you have distance in meters and seconds, time in seconds, so you've got how far something goes and how long it takes. If you divide distance by time, that's your velocity, the average velocity, in meters per second. So you divided your distance by your time, you divided meters by seconds. So with just multiplication and division, that works with units. Don't try to do fancy things, don't try to integrate a farad, but multiplication and division, it works just fine. So there's a standard set of units called SI units that are used by science everywhere. You've got your kilogram, you've got your second, you've got your ampere. I was surprised too, I thought it'd be the coulomb, but no, the ampere is the fundamental unit, and so forth. If we break down the ohm and the farad in just the base SI units, the ohm equals a kilogram times meter squared over a second cubed times an ampere squared. And the proper way to say it is a kilogram meter squared per second cubed ampere squared. Sort of like you might have a unit that's a kilogram meter squared per second squared. I believe that's the Newton, if I recall. But in any case, that's just the way it's generally said. You can say it however you want, but that's how I've always heard it. And you're thinking electric resistance, and now we've got kilograms and cubed seconds, and what in the world is going on? Let me tell you, when I get done with my 9-year graduate course of physics, I'll let you know. Also known as, let's take the smart people's word for it. A farad is a second to the fourth power times an ampere squared over meters squared times a kilogram. Now I've got capacitance and we're dividing by kilograms. I don't know if this is funny to anyone else, but it's funny to me. No doubt, if you were actually in some sort of physics course and you were deriving these units from their fundamental properties in the first few weeks of class, then this would be perfectly natural and make sense to you. I have done enough physics that this doesn't look nonsensical because I've seen how some units are derived. But it still looks funny. Seconds to the fourth power divided by kilograms. It just makes me giggle. But let's multiply them. So if we put this up here, multiplied by seconds to the fourth times ampere squared over meters squared times kilograms. This is ohms times farad. So I mentioned this works, treating these like variables works as long as you're only doing multiplication and division. Don't do fancy stuff with units, but it becomes obvious that this turns out to be nice and even because we had kilograms on the top and bottom, ampere squared on the top and bottom, meter squared on the top and bottom. Seconds to the fourth divided by seconds to the third is just seconds. So it works. It actually works. I just wanted to show that off. You never need to know that. This is the kind of thing that you learn for nerd Trivial Pursuit. I love it. So in any case, the point of this whole thing was that we have our charge and discharge curves. And we'll label that as charge and discharge. So what does it look like if you charge a capacitor and leave it there? Charge and stay. But what if you charge it for a little bit and then you discharge it? It goes like this. Now what if you do that in rapid succession? You get this, roughly. I'm not a draftsman, but you can see that you can make periodic patterns out of it. What happens if you abort? So you want to charge it all the way, but you stop. And then you want to discharge it all the way, but you stop. And then you start charging it again. It gets sharper. What if you only let it charge a little bit? See, the amplitude's lower, it's never charging up enough, but it's getting to be a rather sawtooth thing. This arrangement is called a low-pass filter, if you recall from me showing you the Fourier stuff. And we'll do this in another video on the oscilloscope with real components so you can see it in action. But basically this is a low-pass filter. If you take the voltage here, so this is your low-pass filter, the positive and negative is your signal in, and this is your signal out. Like I said, I'll demonstrate it later, but this is a low-pass filter. That's how you wire it up. If instead, put it the other way, and there's different ways you can wire it up, but this is the way that you generally see it drawn in textbooks. You take this voltage. So what is this voltage? Well, let's say the switch is open. There's no current. The capacitor is discharged. Nothing's going on in the circuit. So the voltage is going to be 0. There's no voltage applied. Let's close the switch. So now you've got 5 volts here and 0 volts here. But the capacitor is taking everything, right? The capacitor is charging, which means there is a current. There's no current through the capacitor, but there's a current from here to here. And then on the other side, let's say we do it from here instead. So the negative electrons are being pushed through the resistor into this end, which is pushing electrons away from this end, back here and through to the negative. So there is a very large current through this resistor. V equals IR, Ohm's law. Large current means large voltage. So if we begin our graph at the beginning at 0, then we open the switch there, and the voltage jumps up because all of a sudden this thing is charging as fast as it can. But then drops back down because this thing is charging, which means it's starting to oppose the current, right? Because a fully charged capacitor in a series arrangement like this is going to stop the DC. It'll effectively pass AC, but DC it'll block. So it eventually tapers down to 0. And of course, your tau time constant is involved here as well. It's going to be down here, 5t, 5 tau, because the capacitor is effectively fully charged at 5 times R times C, which means that it's blocking almost all the current, which means this has low current, which means low voltage because it's V equals I times R. So now the voltage is way down low. So you get that weird spike. So let me draw a graph that has positive and negative. So right now, let's say the switch is open. So we got nothing, and then we close the switch, the capacitor begins to charge, and it goes, right? Capacitor starts to draw a lot of current, which means the resistor has a lot of voltage across it, which goes down to 0. And then we let it sit for a while, and then we set a 0 signal there. So the capacitor discharges. The current goes the other way, because this side charges with negative, this side charges with positive, but it becomes a power source, so it goes the other way. So normally, the current was going this way across the resistor. Now the current is going this way, because this has become essentially this. Because this is always going to be your ground, and this is your signal. Your signal goes high, low, high, low. So right now we've got low, so your positive end wants to go to the negative, so you get a current that goes this way. So just like before, it discharges rapidly and then tapers off, 5 tau. So your whole sequence would look roughly like this. This is called a high-pass filter when you measure across the resistor like this. Does that look familiar to you? Remember when I was explaining high-pass filters in Fourier series against a square wave? What is a square wave in this case? Well, we've got 5 volts and we're turning it on and off and on and off and on and off. Now, in this case, turning it off wouldn't give it a discharge path, so we're essentially turning it off into a 0. But that's what's happening. It charges, discharges, charges, and discharges, because the current goes that way, then that way, then that way, then that way. So this is how an RC network ends up being a high-pass and a low-pass filter. Now, remember your bypass capacitor, where you have, let's say, your positive rail and your negative rail and your chip, your microchip, or whatever. So it takes a positive, it takes a negative, but then you have one of these. Now there's going to be resistance, otherwise you have a short circuit and your system is fried. There could be resistance coming in here. There's certainly resistance in the chip. For it's doing whatever it's doing, there's a load there. That's the point of the chip, right? Whichever way, wherever the resistor is. So this is essentially a low-pass filter. Remember how the Fourier transformation of a DC signal was just a line? Because Fourier is a line, and then a sine wave, and then a tighter sine wave, and then a tighter sine wave, and then they have their own amplitudes and phases and you add them together. But if the only component is that, the bias, that's a DC signal. Now, what if you have a DC signal that looks like this? It's noisy. It's a noisy power rail. The purpose of a bypass capacitor is to smooth that out. Well, the bias of the Fourier series is the lowest frequency there is, isn't it? It's a frequency of 0. It's a line. And then you've got this, and then you got that. So this equals this plus, let's say, some of this plus some of this with different amplitudes, different phases. Imagine you have this nice low frequency horizontal line and then these super small, super high frequency little bits of nonsense that have gotten added in. So a low pass filter allows the low frequency to pass, filters out the noise. And that's not how we conceptually see it. Conceptually, when someone explains a bypass capacitor, they say, well, normally this just holds a charge from the power supply, and anytime the power supply dips, this will make sure it gets its power by supplying it, by being like a battery. And yes, that's also true. Sometimes you'll find there's 7 different ways to explain the same thing, and they're all correct. There's a lot of overlap in life. So in my next video, I will use an oscilloscope to actually demonstrate how you can take a square wave and use this RC network to turn it into other types of waves, using filtering and such. But this is the concept. It's a capacitor and a resistor. If you measure over the capacitor, it's a low-pass filter. If you measure over the resistor, it's a high-pass filter. Your time constant is R times C, resistance times capacitance, which magically works out to seconds. 5 times that number, 5 times R times C, is when we say it's fully charged or fully discharged. And that's all you need to know. So for now, be seeing you.